Thank you.
Yeah, you should be good to go.
Okay, so just starting from the top, this is going to be recitation 3, guys. So here is problem 1. We're going to be sketching the output of y1 of t, and y1 of t is defined here as x1 of t times x2 of t. And then here we further define what those are. So here's x1 of t defined here as the unit step function t plus 2 minus unit step function t minus 4. And here we define x2 of t. So when you see a problem like this, the best thing you can do always by starting is just to graph it. So just to see what we're looking at there. So the first step is looking at like the big picture, and then that's at least what I do. Look at the big picture and then kind of go lower step by step and see like just starting with one step at a time. So here we see the overall question is asking for y1 of t. And we see that y1 of t is composed of x1 of t times x2 of t. So the first step here would be to find out what x1 of t is. And then once we know what that is, we can move on to x2 of t. So here, let's start off with just x1 of t. And like I said, the best thing you can do is always by graphing. So I'll show you 2 different methods. I'm going to go over the second method kind of briefly, but some of my peers last semester had some success with it. I don't like it as much, but I'll still show you it just in case. So here's the method I prefer. So method 1 of graphing. Okay, so we're going to start off by just graphing u of t plus 2. Okay, and here's t. Okay, and does anybody remember from last week? So we have a time shift. So is this plus 2, is it going to be over here or over here? Are we going to shift left or right, guys? Is this going to be t plus 2 to the right or t plus 2 to the left?
Left.
Exactly. How'd you know that?
Because it's inside. So it's the opposite.
It's inside, but it's also positive, right? So you have the right to be negative. So it's t plus 2, so it'll go 2 to the left, right? So this is going to look like this. So in case you forgot what the unit step function normally looks like, it's normally something like this, where here is 0, and then it steps up to 1, okay? So here we're just shifting that whole thing over to the left. So it's going to look something like this. Okay. And it's going to go on like this until infinity. So here, this is going to be 0. And here, at t equals -2, it's going to be 0. So -2 on the right side is equal to 0. -2 on the plus side, going to be equal to 1. And then it's going to equal 1 all the way to infinity. Okay. So here's this graph. And then we're going to go back here to the original equation, guys. And there's this minus sign. So we're going to do a minus sign right here, just so we don't forget. And then we're going to draw the second thing, the second part of x1 of t. So the second component of that is going to be u of t minus 4. So let's graph that now. Okay, and just a little spoiler alert. This one's going to be a shift to the right. Okay, so here it's going to be 4. Okay, so here from -infinity to 4, it's going to be equaling 0. And then at 4 on the right side, is going to be equal to 0. And then 4 on the plus side, going to be equal to 1. And then 1 all the way to infinity, guys, okay? So then now we want to combine these 2 graphs. So normally when you have functions that are constant, meaning they have, 0 slope, you can kind of, almost mentally do it based on, their x coordinates and stuff. So here we see that everything before -2 is 0 for both functions, right? So we don't have to worry about that. So here's -2. They're both 0. 0 minus 0 is 0, right? Okay, so until -2, everything is 0. But then we notice that this guy, once -2 happens, it spikes up to 1. So now one of our functions is changing, so that's when we can kind of assess it. So go like region by region almost. So everything before -2, 0. Then once we hit -2, one of our functions spikes up to 1. So up here, this is going to be 1. On the left side, 1. And that's going to be minus the function on the right side. So can anybody tell me what u of t minus 4 is going to equal at t equals 2. So on the left side, we have u of t plus 2 equaling 1. What is u of t minus 4 going to equal? Anybody have any idea? So here, we can see here, based on our graph, that it's going to just be 0. So we're going to have 1 minus 0, which gives us 1. So here, this is going to hop up to 1. And that nothing is going to change until t equals 4. Because at t equals 4, this guy on the left is still 1. But now on the right, this guy goes from 0 to 1. So once we hit 4, so it's going to be 1 minus 0 until we hit 4. And then once we hit 4, we're going to have 1 on the right side, right? Or on the left side, right? And what are we going to have on the right side? Back down to 0. Perfect, Jade. So we're going to go from 1 minus 0 to 1 minus 1. So now we're going to go back to 0. And these don't change from infinity. So if you kind of want to look at this in a different way, besides graphically, so before -2, they're both 0. Both 0. And then once we hit -2 is when the left guy changes. So we could say from -2 to 4, we could say u of t plus 2 equals 0 or equals 1. And u of t minus 4 equals 0, right? And then once we get t greater than 4, we get that they're both 1. Okay, and as the semester goes on, you'll get really familiar with step functions. I promise you that the key is just to practice. The more you do these types of problems, the better you're going to get. Okay, so the second method, I'm going to just briefly go over it. So something that my peers did last semester is they kind of graphed them on the same plot and then did a reflection for something like this. So what this could look like is and it's better to do this when you have multiple colors or maybe different line styles or something. But here, if we wanted to go back and graph u of t plus 2, looks something like this, right? And then we could go back and graph it on the same plot and do a reflection. So here, we're going to do this whole minus thing in one step. It's going to be one entire step. So we're going to graph this. So this was u of t plus 2. And then by just reflecting it, it looks something like this. So this is going to be minus u of t minus 4. So I don't really recommend this method, but it was something that my peers did last semester. So then once you have this, you're doing this whole minus thing in one function. So then you can just add them, right? So then you can make it this third graph that looks just the adding of them. It's going to overlap here. And then once you get here is when the orange line goes to -1. So adding them, you have 1 plus -1, right? And it goes back down to 0. So I'm not really going to use this method, but it exists. Yep, exactly. So I personally would not recommend it. I think it's way easier to make a mistake with all the minus signs and the plus and the minus signs. I would personally highly recommend to stick with this, but I just wanted to show you guys that there's always more than one way to do things. And once you get more comfortable, you can do things in different ways. But I would highly recommend to just do everything step by step, be very, very methodical. And I promise you, you're not going to make any mistakes. Doing something like this, I feel like you're more likely to make a, miss a minus sign or something and make a silly mistake. So I wouldn't recommend it, but it exists. Okay. Any questions? We're feeling good. So now what this function is going to be is x1 of t. So here we've just figured out what x1 of t is. So we want to make sure to store this. Remember that. So we found x1 of t. Any questions so far? No? We're feeling pretty good? Okay, so now we're going to move on to x2 of t, right? So let's go back to the big picture, right? We're trying to solve for y1 of t. And y1 of t is composed of x1 of t times x2 of t. We just figured out what x1 of t is. Now we need to solve for x2 of t. Okay? So now let's do that. So here we had a minus sign, right? But over here we've got a multiplication sign. So we're going to treat them a little bit differently, right? But the foundation always remains the same. You have two parts for this function. You have e to the minus 4t and just a normal step function u of t, right? And the first step is just to graph both of them without doing any multiplying, subtracting, anything. Just graph all the components individually. And I promise you, you won't make any silly mistakes. So first, let's graph e to the minus 4t. Okay, so it's going to be this decaying function, right? Something like this. It's going to approach infinity. This is t. And here, at t equals 0, right? And once we get to 1, this is probably going to be e to the minus 4. So it's not to scale, it'd be way smaller than that, but you guys get the point. So for the test, if it's the same as last year, you guys won't have calculators, but it always helped in my mind to just do some simple numbers like this. You know what t of 0 is, t of 1 is, just so you help get some scales that. Okay, so now we're going to just do u of t. So you guys are going to be step function professionals. And maybe we'll do it below. Okay. So this is just going to be no amplitude scaling or no shifting or anything. So just a plain step function. This is going to be 1. This is going to be 0. So if we multiply these two things together, maybe I can line up the x-axis for you guys. Does anybody have any guesses for how this is going to look when we multiply them? What should be the first step? How do you think it's going to look?
0.
It's going to be 0 where?
Before
Mm-hmm.
1.
Perfect.
Or before 0.
Mm-hmm. Perfect. How'd you know that?
Since u of t is 0 before t is equal to 0, you know that anything multiplied by 0 is 0.
Mm-hmm. Perfect. Right. So this whole region here is 0. So we're going to multiply this whole region by this whole region, right? Because we're multiplying point by point, and it's all going to be 0. So we can kind of disregard that. So now multiplying that, we get x2 of t. Right? And how is it going to look to the right side of t equals 0? And do we have any guesses?
Like the e to negative 4t, because the step function is just 1. So you know anything multiplied by 1 is just itself.
Isabella, you're a rock star. We're going to turn you into a signals prodigy. Great job. Okay. So it's basically going to look like the exact same thing as this e to the minus 4t, but everything before t equals 0 is going to be 0. And everything after t equals 0 is going to be the exact same. So once again, something like this. But now it's going to be 0. And then here, at t equals 0, it's going to be 1, and then it's going to decay down. And then around 1, it's going to be e to the minus 4. So nothing changes, okay? This is t. Right. Okay, guys. So now we have solved for x of 2t. And earlier we solved for x1 of t. Let me copy it real quick. Here's that. Okay, and the original question was asking us sketch the output of y1 of t, where y1 of t is x1 of t times x2 of t. So we just solved for x2 of t, and earlier we solved for x1 of t. So now all we do is multiply these. Okay. So somebody besides Isabella, how should we go about this? I'll call on people. Don't make me do it, guys. Don't make me do it. How will we go about this? So we have x1 of t and x2 of t. Now we have to multiply them. So let's start off by doing our regions, right? So here, before -2, everything is the exact same, right? Everything is 0, so we don't have to worry about that. But then once we get to -2, our x1 becomes 1. So what do we do from this region, -2 to 0, for both graphs?
Becomes 0.
Right, how'd you know that?
Because everything multiplied by a 0 is a 0.
Perfect. So everything before 0 for x of 2 is 0. So we don't have to worry about it. We can completely disregard it. Even though x1 spikes up to 1, right? Spikes up to 1 right here. x2 of t is still 0. Okay? So everything before t equals 0 is 0. Okay. So now let's work on the region from 0 to 4. So this region right here. So it's just going to be 1, right? So we're going to multiply this region by this region all the way up until 4. They're not to scale. But everything multiplied by 1 is the same, right? So from 0 to 4, it's going to be the exact same. So here, and then up until 4. Okay, and then what happens after 4? X of 1 of t becomes 0. So what do we think happens, guys?
Everything becomes 0.
Perfect. So then this is 0. Okay, so this is how it's going to look. So everything less than 0, so t less than 0, we have y1 of t equals 0. And then we have from 0 to t is less than 4, we get that y1 of t is just equal to e to the minus 4t, and then t greater than 4 back to 0. Okay, any questions, guys? How are we feeling? Does that make sense? I promise you that the more you
Yeah.
practice, the better you're going to get. So yeah, ask questions if you're confused, and yeah, lots of steps. So just let's do a quick recap before we hop to the next person. So the question was to find y1 of t equals x1 of t times x2 of t. The first thing we did was we looked at the definitions for x1 of t and x2 of t, okay? So we looked at those definitions and we broke it down. And then we started by just plotting one thing at a time. So we started off just only plotting the step function for t plus 2. Then we plotted the step function for t minus 4, u of t minus 4. And then we subtracted them, looking at the region by region changes, right? Then we got our x1 of t, and then we moved on to x2 of t, and we saw that here, by just plotting e to the minus 4t and the step function u of t, and everything before 0 was 0 because the step function, there's no shifting, there's no amplitude scaling, so everything before 0 it's going to be 0, everything after 0 it's going to be 1. So basically, everything before 0 you can ignore, and everything after 0 is going to be the exact same as the original function because you're multiplying it, right? So then we got x2 of t, and then the last step was, once we solved for x1 of t and x2 of t, we solve for y1 of t by multiplying them together, okay? So we have kind of this region where, this non-zero region where we can kind of isolate everything outside of this region is 0, and everything inside that region is the same, okay? Any questions, guys? Questions, comments, or concerns? Okay, if you have any questions about this or just in general, you can always email me, ask in the chat. And I'll pass it to the next person.
Alrighty.
Okay.
Stop sharing. Perfect. All right. Can everybody see my screen okay?
Mhm.
All right. So I'm going to be going over linear time invariant systems, aka LTI systems. So linear time invariant systems are very important, specifically later in the semester for some future things you'll learn. You can only apply them to LTI systems. So being able to identify if a system is linear and time invariant is very important. So first we have to define linearity and time invariance. So a system being linear is a combination of two other factors of systems. So you have to consider, does it meet the scaling criteria and does it meet the additivity conditions? So the scaling criteria is if you take an input and you multiply it by some constant, some scalar, the output should also be multiplied by the same constant. And the additivity is if you take two inputs, you add them together, it should give you the same output as if you take two different inputs, run it through the system, and get two different outputs, those should add up to y1 plus y2. And if you take your two inputs, add them together, and then run it through the system, it should give you the same y1 plus y2. And both of those factors combined define a system as linear. So how do we identify linearity? We're going to take two input signals and we're going to verify that they meet both of the criteria, the scaling and additivity criteria. And you do this by creating two input signals and then creating a third input signal and ensuring that the first input signal and the second input signal added together are equivalent to the two outputs added together. And we're going to make sure that the scaling factor is also met. I'm going to do a problem so you can see that in more definitive terms. And then for an LTI system, you also have to show that the system is time invariant, which means that a shift in the input signal is going to lead to a shift in the output signal. So in order to prove this, you add a delay to the input and a delay to the output. And if they're equivalent, you have a time invariant system. So let's jump into a problem. So we're going to identify if the system below, y of t is equal to 5 cosine of 2t x of t, is linear, time variant, or both. I'm going to jump over to my iPad quick. And again, everything from that slideshow should be on Canvas. So if you need to go back and see those steps at any point, you can find it on Canvas. So we have our system. Y of t is equal to 5 cosine of 2t x of t. And we want to determine if it is linear and if it is time invariant. So first we're going to tackle linearity. So we're going to define two input functions, x1 of t and x2 of t. We're going to pass them through our system. And we're going to get two output functions, y1 of t and y2 of t. Now, we can define y1 of t and y2 of t as 5 cosine of 2t times x1 of t for y1 of t, and the same times x2 of t for y2 of t. So those are our outputs when we input our two input functions separately. Now, if we define a third input function, x3 of t, and we're going to define it as a scaled added version of our two inputs. So we're going to use the scalar alpha and beta. So alpha x1 of t plus beta x2 of t is equal to x3 of t. Now we can take that function and we can pass it through our system and say, okay, does this give us the same output as our original inputs separately? So if our output term is equal to the scaled and added version of our two previous outputs, we can say the system is linear. So how do we prove this? We have y3 of t is equal to 5 cosine of 2t x3 of t. And that's again just from up here where we defined our system. So now our x3 of t term we have defined in terms of our x1 and x2. So we can substitute in our defined version of the variable, and we get 5 cosine of 2t times our alpha x1 of t plus our beta x2 of t. And now if we multiply this out, and we distribute the 5 cosine of 2t, we can see that we are given alpha times 5 cosine of 2t x1 of t plus beta 5 cosine of 2t x2 of t. And now you can see that this term and this term we have defined above as our outputs from when we inputted them separately. So we get y1 of t is equal to 5 cosine 2t x1 of t, and y2 of t is equal to 5 cosine 2t x2 of t, which is the same thing we have down here, but scaled. So we can redefine this in terms of our previous outputs. And we can see that y3 of t is equal to alpha y1 of t plus beta y2 of t, which we said earlier up here. We said that if that was the case, the system is linear. So we can say with confidence that therefore system is linear. Does anybody have any questions about that? Go ahead and throw them in the chat or speak up if you have any questions. All right, I'm going to jump into time and variance then. And let me know if you have any questions. I would consider time and variance to be more conceptually challenging to prove. So feel free to ask any questions if you need to. So we're once again going to define our two inputs, x1 of t and x2 of t, pass them through our system. And get y1 of t and y2 of t. As we put them through the same system, our output functions are going to be the same as they were before. we're going to get 5 cosine of 2t x1 of t. We're going to get y2 of t is equal to 5 cosine of 2t x2 of t. Now, in order to prove that a system is time invariant, we have to shift the input and the output and verify that they're the same. So let's define, I'm going to move over here a little bit so we're not bothered by our other work. So let's let x2 of t be equal to x1 of t minus t naught. So now we're taking x1 of t and we're shifting it in the time domain. And we're going to say if our output for y2 of t is equivalent to the shifted output of y1 of t, so y1 of t minus t naught, then the system is time invariant. So let's set about proving that. So we know that our y2 of t is equal to 5 cosine of 2t x2 of t. And we just defined that x2 of t is equal to x1 of t minus t naught. So we can substitute that in for x2 of t, and we get y2 of t is equal to 5 cosine of 2t x1 of t minus t naught. So now we have our y2 value. We know that y2 of t is equal to 5 cosine of 2t x1 of t minus t naught. Now we need to determine what y1 of t minus t. So we know that our y1 term is equal to 5 cosine of 2t x1 of t. So now we're going to apply a shift to this. And I want to ask y'all, do y'all think this is going to be equivalent to our y2 of t, or you think this is going to be different from our y2 of t? All right. Megan believes it's going to be different. Does anybody else want to weigh in? That is understandable. All right, I'm going to continue. And Megan is actually correct. So because we are applying this after, and we are shifting it from y1 of t to y1 of t minus t naught, we actually have to shift each t value. Whereas before, we simply substituted in our x2 value. Now we have to shift each value of t, which is going to make these two not equivalent. So y2 of t does not equal y1 of t minus t naught. Therefore, system is time invariant. So we determined that the system is both linear and time variant. So this would not be classified as an LTI system, as both criteria have to be met in that case. Does that make sense? Do we have any questions? I'm happy to go back over any part of this.
So for the part about like the testing linearity, when you do the combined equation to test, if you were to get it like it shows that it's not linear, that test doesn't tell you which part of it doesn't meet, right? Like it will just tell you it's not equal, but you'd have to do the test separately to figure it out independently.
Well, if you're just testing for if it's linear or not, you can do this and it'll say, okay, the system is linear or the system is not linear. If you want to test if it's scaling or additive separately, you would have to do each individually. Is that what you were asking?
Yeah, my question was basically like, yeah, if you were testing linearity, but you get it that it's non-linear, but you wanted to know which, like if it was not scaling or if it was not additive, you wouldn't be able to tell from the combined equation, correct?
It would be best to go and do the tests independently.
Okay.
Yes.
Only if you're really curious which one it's failing. In general, for example, as a again, in real life, I think, Jade, your question is more relevant because you might want to know which one is not being, is being violated. But as far as exams and homeworks go, if we ask for linearity, that would be enough for you to just do it. In general, though, you can, as you apply the definition, you can kind of figure out which one's failing, whether it's the additivity or the scaling that's failing, depending upon the definition. For example, if you have x squared, right, then that's an additivity problem for sure, because sum of squares is not same as square of sums, that kind of a thing.
Okay, sounds good.
Perfect. Does anybody else have any other questions? Okay, I would just recommend, I'll take a lot of time doing this on the homework and make sure that you really understand it, because especially the time variance can be rather tricky to wrap your head around in terms of the math and proving it. So just make sure you really are comfortable and you know what you're doing before the exam comes. Even if you have to go back and redo that question on the homework, just to make sure you know it, I would recommend that. Awesome. There's no other questions. I'm going to pass it off. If you have anything else, feel free to type it in the chat and I will answer it.
Hi everyone, can you hear me?
Yeah.
Cool, thanks for coming again. I'm happy to see you all today. And I'm gonna cover the last topic of tonight. Let's look at the last question we have on recitation. So, okay. Can you see my screen?
Yeah, we can, Alpha.
Cool. So I'm not using whiteboard today, but if you feel like you want to help me write something, you can go on the top of the screen. You see annotate, and you can still draw stuff on there too. But I'm gonna just draw on my note here. All right, let's go. So, okay, we're gonna talk about system property today. And there are gonna be 4 properties that we will cover today is stability, causality, memoryless, and invertible. So let's start at the stability of the system. how do we know if the system is stable or not? So when we talk about the stability of the system, we usually just focus on the amplitude translation. So if we have yt equal ax alpha t plus beta plus b, amplitude translation means that we're gonna focus on A and on B, and we're gonna check that can they go to infinity. If either A or B can go to infinity, that means that the system is unstable and unbound. But if it doesn't, it means the system is stable. Okay, and let's look at the question we have here. So we started off as yt equal t squared x 2t. Can anyone help me point out what is the amplitude in this term, please? Or like circling around the amplitude term. Anyone? Anyone want to try this? Thank you, Isabella. Yes, you're right. So t squared is gonna be our amplitude. And can t squared go to infinity? We don't know what is t, right? That means there is gonna be any probability that t can be infinity, and we don't know what it is. Therefore, yes, right, Jade. This system, because t can go to infinity, that means that the system is unbounded. And by being unbounded, it means the system is unstable. Therefore, it means that this system is unstable. Now, I have a question for you in this case too. Let's say if I have like yt equal cos t, like say t, let's just do a number here, 5 cos t. Is this system stable? Anyone want to answer this?
Yes, it is.
I'll give you a hint. You need to look at this term. Anyone want to try answer? Wait, in the chat. I see the chat.
I think Benjamin was saying something. I think he said that he thinks it is stable, right?
Yes, it is stable. Thank you. The reason that this is stable is because, like, okay, we know that this is cos t, right? And wait, this is sine t, cos t. The value is gonna bound between 1 and -1. Therefore, we know for sure that the system is bounded. And it's not gonna approach infinity. Therefore, yes, this system is stable. All right.
So when you say bounded, does it mean between the y-axis or is it both the y and the x?
The y-axis, yeah, it's gonna be, let's say it's gonna be the output that is bounded. Like, and it doesn't go to infinity. Yeah, let's say it's output. Do you have any more question on this? Let's see the chat. Is this topic gonna be on next week quiz? I'm sorry. Wait, Professor, is this gonna be on the quiz? Oh yeah, it is. It's gonna be on the quiz. So prepare everyone. All right. If we're good with the stability of the system now, let's move on to the causality of the system. So when we wanna like know if any system is causal or not, we want to know if the system does it depend on the past value and the present value. Like we know if something can cause something, it has to like have the effect from the past or either the present. So if our system depends on the past value, yeah, it's causal. And our system depends on the present value, yeah, it's causal. However, if we have our system that is dependent on the future value, this is not causal. And the way that we can check the causality of the system is to check in these three cases, three scenarios. We can check when t is 0, when t is negative number, and when t is positive number. Okay, let's do this, everyone. Let's do this together. All right, let's check on the first step then. So can anyone help me here? Fill in here. What is gonna be yt when t is 0? So what is y0 gonna be here?
Would it be causal?
Yeah, it's gonna be causal if we have t equals 0. So 0 squared and x equals 0 here. So 0 and 0. It's still causal, right? Okay, let's check for another step. What if we have t equal -1? Anyone would like to?
It would be causal.
Yeah, it's gonna be causal, right, Ruhi? So like what we have here is still in the past. It's still gonna be causal. However, when we talk, now let's try when t equal positive number. Is it gonna still be causal?
It would not be causal.
Yes, right. It's not gonna be causal anymore. So because now we originally have t equal 2, right? But when t equal t, but when we have t equal 2, we're gonna get x4. But 4 is more than 2 here. Therefore, this system, when we put t equal 2 inside, we can see that the output depends on future value. Therefore, it's not causal. That means that the system that we have here is not causal. All right. Anyone have questions on this?
That was very nicely done, Alpha.
Thank you, Professor. All right. Okay, if you don't have any question on that, let's move to the next property. Memoryless. What does it mean when the system is memoryless? When the system is memoryless, it means that the output depends only on the present value. And that means it's memoryless. Okay, let me highlight on this. Output depends on present value. Memoryless. And from the causality test here, we can see that y2 equal to something x4 here. So at time equal to, we got xt as x4. That means that our system, the output of our system depends on the future value and is not dependent on the present. Therefore, we can say the system is not memoryless. And by saying the system is not memoryless, it means that the system has memory. So, and there's also one thing that I want to mark with everyone. So sometimes, actually when we see a system that is memoryless, it's gonna be causal, because it depends on the present, right? However, when we see a system that is causal, it doesn't always mean that the system is memoryless. Can anyone help point out to me why is that not the case? Can you remember what's the criteria for a system to be causal? It's gonna be dependent on did and did. Can anyone help me fill in the blank? I'll give you a hint on first letter.
Is it present and past?
Yes, thank you. And thank you, Isabella, in the chat too. I have difficulty seeing chat right now. But okay, thanks for your answer. It's gonna be, okay, so a system that is causal is gonna depend on past and present, like Isabella and Rui said. Good. But we know that memoryless also only depends on present, right? Therefore, yeah, a system that is memoryless is causal. But causal, that is a system that depends on present and past, doesn't necessarily mean it's memoryless. Okay, so we can say that our system in this question is not memoryless, therefore it has memory. Cool, and let's move on to our last system property. Invertibility of the system. So what does it mean if a system is invertible or not? Let's say if I have an input xt and I put it in some system h, and I will get the output yt, right? And when I put the output yt into the inverse of the same system, I will expect to get the same xt. Like, okay, if for every output yt, there exists a unique input xt. So only one xt for only one yt. And if we see a system that has multiple yt or multiple xt, and it's not like 1-on-1 ratio, it's not gonna be invertible. And we can also make some visualization with graph here. I need to give credits to Amelia here. She helped me explaining with the graph here. So big claps to Amelia. Okay, if we say we have a linear graph here, we see that let's say this is y and this is x, but on your exam it can be output and input, so or can be x and t. You need to like be able to identify which one is input and output. So in this graph we can see that we only have one x for one y. Therefore, this is invertible. The system is invertible. However, if you see a parabolic graph like this, okay, let me make this straight line. Oh, okay. Let's say if I have one y here, we will spot two values of x, right? x1 and x2. Therefore, this system is not invertible. Okay, now after we know the definition of invertibility of the system, let's look at our question. Is this system invertible or not? Anyone want to give a shoot here? Do you want to make a guess? TikTok. I would say no because of squared t. Thank you, Jade. You almost right. Almost right, Jade. Actually, I think this tricks a lot of people. I got tricked by this too. Because actually, t squared is only amplitude. And it doesn't affect the invertibility of yt and x2t. So this is just amplitude, but the real thing that yt is dependent on is x2t. So there are two scenarios to answer to this question actually. Actually, this system can be both vertible and invertible, depends on what we set the t to. But yeah, for example, okay, if we have xt at if we have xt as t to the power of 4, because we don't know what x2t is, right? We don't know what this is. It doesn't specify to us on the question, so we gotta be careful. If we have like xt equal t to the power of 4, x2t gonna be 16 t to the power of 4. In this case, it's gonna be non-invertible. Because, yeah, it's non-linear. Also, if we have this case, when xt equal to t, and x2t is gonna be 2t, right? So yt equal t squared. We're not gonna look at this because it's just amplitude equal to t. This is gonna be linear. Therefore, in this case, it is invertible.
So may I step in for a moment?
Yes, please, Professor.
So important thing to remember here is that we are looking at the property of the system and not the signal itself. So in terms of invertibility, what we are saying is that if we can identify a one-to-one mapping between the X and the Y, that's enough for us, right? So the question to ask is, could this Y come from two different values of X of t? So what you can do is you can now kind of solve for X of t, right? So you can go back and say X of 2t is Y of t divided by t squared, right? And then X of t would be, going back to from 2t to t. So, you're kind of halving the t. So you would kind of be 4 over t squared y of t half. And then now you can ask the question, can the same xt, or rather can two different x of t for a given t, for different values of t lead to the same of yt? So because it only involves the relationship between the y and the x, unless there is a confounding factor like a power on the x input term itself, in general, it's going to be invertible. Okay.
Thank you,
So
Professor.
I hope that part was clear.
Yeah, if there's confounding variables such as, like Professor said, square on t, and now we don't know for sure if x is positive or negative, it's not going to be one-on-one mapping anymore. Therefore, it's going to be not invertible.
No, I'm saying it is invertible regardless of all of that, because you have to kind of look at ask the simple question, can I have two different x's for the same y in a generic sense? Okay. So this is a system definition, not a signal definition. So that's why you have to ask that question. Can I have, so unless you have the x term itself in the y of t system definition, squared or some other ambiguous thing like cosine thereof and things like that, that might throw off the actual x or multiple x's giving rise to the same or leading to the same y. For example, if it was cosine of x of t, for example, y of t equals cosine of x of t, right? So now multiple values of x of t can all lead to the same y, regardless of what x of t looks like. We don't even care what x of t looks like. Multiple values of x of t, whenever the signal x of t is let's say pi or 3 pi, it will still give you the same y. Sorry, there was a question. That's right, Jade, because the square term is just an amplitude scaling factor here. The x, the input itself, is what you need to ask about.
So basically something is not invertible if it has the same y for two x's or more?
That's right.
Okay, thank you.
Sure.
Cool. Thank you, Professor.
You're welcome.
All right. Anyone have more question on this part? I believe that's the end of my content today, but I will stay here for a little bit more if you want me to revise in the previous part, or if you have any more questions.
Jade would like you to go over causality again, I
causality. Okay,
Yeah.
let's go. So for a system that is causal, the output of the system, yt, is gonna depend on the past and on the present of the input. Therefore, if we see the output that is dependent on the future value, this is not causal. So we can only expect to see a causal system, and it only depends on past and present value. And the way that we can check the causality of the system is check when t equals 0 and when t equal negative number and when t is positive number. And from our checking, it seems like the system that we have right now, when we plug in t equal 2 into the system, we see that the output is dependent on the future. And by the definition of causality of the system, if the system is dependent, the output of the system is dependent on the future value of the input, that system is non-causal. Therefore, we bring into this conclusion that this system is not causal. Let's say, for example, if I have this system, yt equal 15 xt minus 8, is this system causal or not? Is it gonna be causal? Yes, thank you, Jay. It is causal because t minus 8 is the past value of the input. Therefore, it is causal. All right. Do you have more question, or do you still need more clarification on this?
No, I think it makes sense now. And then when you talked about whether this system has memory or not, what did you say that it is memoryless or that it has memory?
Okay, it's gonna be this part, this big part. So when I say a system is memoryless, I want you to know that that system is also causal. However, if we have a system that is causal, we cannot bring into the conclusion that the same system is memoryless. It's gonna be memoryless, then causal. But if it's causal, it's not necessarily memoryless.
Okay. And then so if we were to try to like figure out the last problem that we just went over, if it was memoryless or not, for
Okay.
I think it was problem 6 that you showed for the one about causality.
Problem 6. This causality?
Yeah.
Causality?
Like for this system, would it be considered memoryless, or does it have a memory?
This one, right? You mean this
Yeah,
one?
yeah.
Okay, let's try it together, everyone. Is this system, you are asking if this system is memoryless or not, right?
Yeah.
Okay, let's try it together. I cannot remember. Not is it 15, right? X t minus 8. Okay. And when I say something is memoryless, it means that the system only depends on present. And we see that this system is also dependent on the past. Therefore, what does it mean? If it also depends on the past and not only the present. Memoryless, yes or no? Yes, it's not memoryless. Thank you, Isabella. It has memory. Yeah, this system gonna have memory. That's right.
How do you know if it depends on the past or not?
So say if I have like years, because it -8 t at 8 second, t at 8 time units ago. So that is like the past. But if I have like xt at some time in the future, this is future.
So the one we did before with the t squared x 2t, that was memoryless.
T square x 2t,
Yeah.
is this memoryless? This system is not memoryless here because, okay, let's try this together. It's not gonna be memoryless. I think I should move on to next paper so we can see this clearly. You mean this same one, right? Yt equal t square x2t. Is it memoryless? So I do feel that sometimes too, if I'm like feeling like memoryless system. I just feel like we have a lot of content that we go over today, but take some rest. And I think your brain will form some memory tonight. Yeah, strengthen your neuron connections, everyone. Oh my God, William Hack, why you feel so depressed? Okay, is this system memoryless? Like I said, t squared is only just amplitude, right? So we're just gonna present that this doesn't exist. It's just amplitude. The real dependent output is dependent on x to t as an input. And from this part, this 2t part here is double of the time, right? That means that it's sometimes in the future. And also that means future, not dependent only on the present, therefore is not memoryless. And that means this system has memory. Cool. And you got any more question? I suggest, because when I had midterm on this topic, I get so much confused. Like there are so many system properties. And when I got on the exam, and I didn't sleep in my midterm exam. I didn't sleep before I went to midterm exam, and I got this very confused. That's why it's important to sleep, everyone. Be sure you sleep before your midterm exam. So on the exam, I got confused between system, like different properties, right? So I want you to make sure you understand and can remember how do you test if this system, if the system on your exam have the certain type of property that you want. Maybe you can try like writing them out or try making examples, like weird example in the that we don't have in homework today, and try it with yourself, try it with your friends, and see if you can tell if the system has the specific properties that you want to test or not. It's gonna help you a lot on the exam and save stress. Cool. I'm glad I can help, Jade. All right. I think that, that's the last part of this recitation, because I have the last question and also the last topic. Yeah. And also, I just want to make sure in this question is invertible, because this thing is, one-on-one mapping, linear, and we just treat t square as amplitude. Cool. You're welcome, Heidi. You're welcome, Benjamin. Thanks everyone for coming.
Anybody else have any questions? Follow up
Yeah.
about the recitation or anything?
On the previous part.